Right now, somewhere in the world, a human embryo is growing a tail. Not a metaphorical one, an actual physical tail complete with its own set of tiny vertebrae sticking out from the base of the spine like something straight out of a monster movie. And here's the part that should really mess with you. Every single human embryo does this. Yours did too. Mine did too. And by the end of this video, you'll understand exactly why that tail disappears before you're even born, and why the scientific answer to that mystery only got solved a few years ago, thanks to one exhausted graduate student, a broken jar, and a seriously unlucky cut on his finger. Let's start with the weird part nobody tells you in biology class. Around 4 to 5 weeks into human development, embryos grow what's technically called a tail bud, a genuine tail structure with somewhere between 10 and 12 vertebrae. For a brief window, human embryos look startlingly similar to embryos of other tailed animals, fish, mice, even other primates. Then, over the following weeks, that tail gets reabsorbed back into the body, its cells repurposed, its length shrinking down until all that's left is a small cluster of fused vertebrae at the base of your spine. You know it today as the coccyx, or if you've ever fallen hard on your backside, you know it as that one bone that ruins your whole week. Every human alive today is walking around with the leftover architecture of a tail we simply never finished building, which raises the obvious question: why does the tail get switched off partway through development? And more importantly, why did our ancestors lose it in the first place? For a long time, the explanations people offered were mostly educated guesswork dressed up as science. Maybe tails just became less necessary as body size increased. Maybe they were an energy drain not worth carrying around anymore. These ideas weren't unreasonable, but none of them were actually testable in any rigorous way, and none of them explain the specific genetic mechanism that made tail loss happen in the first place. You can theorize about why evolution might favor something all day long, but without finding the actual molecular switch involved, you're really just telling an educated story, not proving one. Here's where we need to zoom out. Almost every vertebrate on the planet has a tail. Fish have them, reptiles have them, the vast majority of mammals have them, including most primates. Monkeys swing through trees with long, dramatic tails trailing behind them, sometimes even using them like a functional extra limb. New World monkeys in Central and South America take that concept to an extreme, evolving prehensile tails strong and dexterous enough to grip branches and support their entire body weight, essentially turning the tail into a fifth hand. And then you get to the apes: gibbons, orangutans, gorillas, chimpanzees, bonobos, and us. Not a single tail among any of them. Somewhere around 25 million years ago, the common ancestor of all apes lost its tail completely, and every single descendant species inherited that same tailless body plan. That's a strange thing to happen to an entire branch of the primate family tree, and for decades, scientists genuinely had no idea what caused it at a genetic level. They could see the pattern in the fossil record, they just couldn't explain the actual biological switch that flipped. It's worth pausing on just how useful tails actually are for the animals that kept them, because losing one wasn't some obviously smart upgrade. Old world monkeys use their tails constantly for balance, sprinting along branches, leaping between trees, correcting their posture mid-air the way a tightrope walker uses a balance pole. New World monkeys took things even further, some species evolving tails strong enough to hang their entire body weight from a branch while both hands stay free to eat, groom, or grab a snack from a neighboring tree. In a lot of ways, a tail is a phenomenally efficient piece of biological engineering, which makes it even stranger that an entire lineage of primates just walked away from that advantage entirely. That mystery sat mostly unsolved for a surprisingly long time until an accident in a New York apartment cracked it wide open. In 2019, a graduate student named Bo Xia was cleaning up his kitchen when he cut his finger on a piece of broken glass. Nothing dramatic, just an annoying trip to the emergency room and a handful of stitches. But sitting in that waiting room, nursing his hand and presumably bored out of his mind, Xia started thinking about scar tissue, about how differently various animals regenerate damaged body parts, and about how some species can even regrow entire limbs while humans are stuck forming scars instead. That train of thought eventually spiraled into a much bigger question about lost body parts in general, and somewhere down that rabbit hole, he landed squarely on the tail. It's a genuinely wonderful example of how scientific discovery actually works sometimes, which is to say, not through some grand planned research proposal, but through a bored, mildly injured person staring at a waiting room wall, chasing one curious thought to its logical extreme. Shia reportedly went home that same night and started reading everything he could find about tail loss in primates, which is either the most productive reaction to a minor injury in scientific history or a sign that graduate school does strange things to a person's relationship with free time, possibly both. Here's the twist that turned an ER visit into a genuine scientific breakthrough. Shia, working alongside researchers including Itai Yanai at NYU, started digging into a gene called TBXT, a gene long known to play a critical role in tail development across vertebrates. When they compared the TBXT gene across tailed primates and tailless apes, they found something unexpected sitting inside it. A small chunk of extra genetic material called an ALU element had inserted itself into the gene at some point in ape evolutionary history. ALU elements are sometimes nicknamed jumping genes because they're small, mobile pieces of DNA capable of copying themselves and inserting into new locations throughout the genome, often without causing any noticeable effect at all. In fact, the human genome is absolutely packed with these things, over 1 million copies scattered throughout our DNA, the overwhelming majority of them just sitting there quietly doing essentially nothing of consequence. Except this time, it did cause an effect, a big one. That ALU insertion sat right in a spot that interfered with how the gene gets processed, triggering something called alternative splicing. In simple terms, the cell's machinery started reading and assembling the gene's instructions slightly differently, producing a shortened, altered version of the TBXT protein. And that altered version appears to disrupt tail formation during embryonic development. Naturally, the researchers didn't just want a compelling story sitting in a genome comparison. They wanted proof, the kind that actually holds up under scrutiny rather than just sounding convincing in a research meeting. So they took this specific genetic change and engineered it directly into mice, and the mice grew little to no tails. Let that sink in for a second. A single specific genetic tweak, isolated by researchers chasing a hunch that started with a kitchen accident, was enough to dramatically shorten or completely eliminate tails in laboratory mice. That's about as close to solving a 25-million-year-old evolutionary mystery as modern genetics gets. But here's the twist inside the twist, and honestly, this is the part that makes the whole story so much darker and more interesting than a simple "we found the tail gene" headline. The mice with this engineered mutation didn't just lose their tails cleanly. Some of them also developed neural tube defects, the same broad category of birth defect responsible for conditions like spina bifida in humans, where the spinal column doesn't close properly during development. In other words, the mutation that likely helped our ancestors lose their tails may have come bundled with a real biological cost, not a clean upgrade, a trade-off. And this isn't just an abstract footnote about ancient ape evolution either. Neural tube defects are still a real ongoing concern in human pregnancies today, affecting a meaningful number of births worldwide every single year, which is exactly why doctors emphasize folate intake so heavily during pregnancy in the first place. It's genuinely strange to consider that a small genetic scar left over from a 25-million-year-old mutation might still, in some roundabout evolutionary sense, be tangled up with a modern medical concern that expecting parents are warned about at every prenatal appointment. Think about what that implies. Somewhere around 25 million years ago, a genetic change swept through the ancestral ape population, a change that removed the tail, but simultaneously nudged up the risk of a serious developmental defect. And it stuck around anyway. It spread through the entire lineage, becoming permanent in every ape species that came after, humans absolutely included. Which means whatever advantage came with losing the tail must have been significant enough to outweigh that increased risk, generation after generation, for millions of years. So what was that advantage? This is where the story shifts from pure genetics into behavior and locomotion. And honestly, it makes a lot of sense once you picture it. Around the time apes lost their tails, their movement style was shifting dramatically. Monkeys tend to move quadrupeds along the tops of branches, using a long tail as a counterbalance while running and leaping. Apes, on the other hand, increasingly relied on a completely different strategy called suspensory locomotion, essentially swinging below branches using their arms, a style you can still watch gibbons perform today with genuinely alarming speed and precision. A balancing tail becomes a lot less useful when you're hanging beneath a branch instead of running along the top of one. In fact, a long trailing tail might have actively gotten in the way, a dangling liability rather than a helpful counterweight. Losing it may have streamlined this new style of movement, freeing up energy and reducing unnecessary weight for a body plan that was rapidly specializing toward upper body strength and shoulder mobility instead of tail-based balance. Watch footage of a gibbon flying arm over arm through a rainforest canopy sometime, and it becomes fairly obvious pretty quickly that a long, dangling tail would be less of a helpful accessory and more of an unfortunate way to get tangled in a branch mid-swing. But the story doesn't end there. The loss of the tail didn't just change how our ancestors moved through the trees. Many scientists believe it laid the foundation for one of the biggest turning points in human evolution. As apes shifted from running on branches to climbing vertically and swinging beneath them, a long balancing tail became less useful. Over millions of years, their bodies adapted to this new style of movement, and those changes may have opened the door to something extraordinary. Walking upright. Once our ancestors stood on two legs, their hands were finally free to carry food, create tools, build shelters, and eventually shape entire civilizations. In a surprising way, one tiny genetic change may have helped set the stage for everything that makes us human today. But evolution never gives without taking something in return. Even today, in extremely rare cases, some babies are born with what doctors call a vestigial human tail, a small soft tissue extension near the tailbone. It usually contains no true vertebrae and can be removed surgically, but its existence reminds us that the ancient genetic blueprint for building a tail has never completely disappeared. It's still hidden inside our DNA, almost silent, waiting for a rare moment to reveal itself. So the next time you feel your tailbone after sitting too long, remember, you aren't touching just another bone. You're touching the final remnant of a body part your ancestors relied on for millions of years. A tiny piece of evolutionary history that still lives inside every one of us. If this story surprised you, type tailbone in the comments, because sometimes the biggest changes in the history of life begin with the smallest accidents. Around 25 million years ago, a tiny piece of jumping DNA landed in just the right place, permanently changing the future of every ape that followed, including us. No grand design, no dramatic event. Just one microscopic genetic accident that quietly shaped the course of human evolution forever.